Okay, so Lynn, can you please go now to slide 23?
Okay.
Now concerning the comparison in net energy ratio. So also the results were experimental.
Yes.
And can you just talk a little about the variation between the different types?
Between the three liquid biofuels?
Yes, so any physical
Yes.
interpretation of this?
Yeah, so as we mentioned earlier, the third generation bio-oil requires a lot of energy, which is why, as we can see in this graph, it has the highest NER. And we wanted to be more less than one, since it's the ratio basically of how much energy we're putting into the system versus how much we're generating. So we wanted to be less than one. And as we can see, the only one which has an NER less than one is the biodiesel, which is why we picked it to be the most favorable when it's come to the NER.
Okay, thank you. Now, Jana, can you go please to the next slide? Okay. Jana, here, concerning water requirement, can you talk a little about the comparison?
Okay, so similarly, we mentioned that the biofuel requires a lot of water. So if we look at the graph, it has a much larger amount compared to the others. And this is because the microalgae requires a lot of water for their growth and cultivation, while the biodiesel also requires more water than bioethanol, since it requires a lot of irrigation water to obtain the plants and vegetables for the biomass of the biodiesel production. And meanwhile, bioethanol requires the least amount of water, which is why we picked it as the most favorable.
Okay. And please, concerning the economical analysis, Jana, can you tell me on what basis they did the economical analysis? The factors were common, or for each type they did a certain economic viability study different than the other?
Yes, so basically, to obtain this graph, we first got the different production costs to produce each of the three. So this includes, for example, the raw material cost, the labor, the maintenance, and the land, and all of these costs. And then we looked for and references for the selling price of each of the three biofuel, and we compared how much it would be, the total production cost would be, and we found that it is the highest for the third generation biofuel, and it's also much larger compared to the two others.
Okay.
And bioethanol has the least.
Yes, did you
Yeah.
consider the confidence in future and risk analysis in your study, in your economical study?
No,
Not
we didn't.
really.
That's why we added it in a limitation as something that we should have considered. Because it is very important to, first of all, identify the supply and demand of each biofuel and its corresponding conventional fuel, and to determine the risk associated with implementing these biofuels and all of that. So this is also very important to consider, but we added it as a limitation because we were unable to do it for this review paper.
Okay. Thank you so much.
You're
You're
welcome.
welcome.
Okay. So next group now.
Yes, I'll be sharing my screen.
Yeah, you can share.
Okay, so
Can
hello
you see it?
everyone. My name is Karim Osman, and my group partner is Sharif Kanaan. And today we'll be presenting our project on the effect of Bitcoin on the environment. Next slide, please. Okay, so starting with the outline. We'll start off with an introduction on the subject. We'll then try to define Bitcoin and blockchain in a clear way. We'll then look at the different types of mining and different types of hardware which is used in the mining process. We'll then take a look at data on the environmental impact of Bitcoin mining. We'll also go more in detail into what types of cooling are used in Bitcoin mining facilities. And finally, we'll see what type of role does renewable energy play in Bitcoin mining. And finally, we'll take a look at two different case studies. The first one being mining with wind farm, and the second one being Bitcoin mining, a sustainable heating model.
Okay, so in recent years, cryptocurrency has taken the world by storm, and it invaded the top stories of news articles around us. So, for example, Tesla, one of the main companies led by Musk and viewed by many as the face of our future society, recently made a substantial investment of $1.5 billion into Bitcoin, which is the most well-known cryptocurrency today. And similarly to any type of resource, cryptocurrency requires harvesting, or what is referred to as mining. And behind its digital nature lies a very real impact on the environment. So the carbon footprint it leaves behind has become magnified and the subject of much scrutiny, which is why we have decided to have our project on this topic. And a fun fact is that Bitcoin's growth is since 2009 is around 210 million%. So that's it.
Okay, so now starting with the definitions. First, let's take a look at what Bitcoin is exactly. Well, Bitcoin was the first cryptocurrency ever established. It was launched back in 2008 by a group or a person, we still don't know yet, which used the pseudonym Satoshi Nakamoto. It launched it with a paper explaining what Bitcoin was. In this paper, it explained that Bitcoin will be a cryptocurrency which is decentralized, which means this currency is fully digital and it does not follow a certain regulating authority. It is based on a program which runs by itself and does not need any types of intervention. Its supply is limited and it's fixed at 21 million Bitcoins. We will later explain why was this choice made, but basically it's done to prevent inflation and loss of value in the currency. The invention of Bitcoin was the first example of blockchain technology, and we'll explain in the next slide what exactly is blockchain technology. As Sharif mentioned, Bitcoin is the world's most important cryptocurrency today, both in terms of market capitalization and dominance. So what does this mean? Today, Bitcoin is valued, or one Bitcoin is valued at approximately $62,000. And in terms of market capital, it is approximately at $1.2 trillion. And the whole cryptocurrency market is at $1.7 trillion. So you can see how much Bitcoin is dominating the market.
Okay, so I define the blockchain. Forbes defines it as a distributed ledger that records transactions in a code. So in other words, each transaction gets recorded in a virtual block, if you want, and this block gets linked to other blocks of transactions, creating a chain referred to as the blockchain. And to keep the blockchain accurate and reliable, an extremely large number of people, literally anyone who wants to, can keep an updated copy of it all over the world, hence creating a cohesive transaction record. But inevitably, and the blockchain is prone to discrepancies because of internet problems, to delay. So transaction requests can be recorded in different orders within different ledgers. So to avoid this, the proof of work system was created, where it consists in solving a mathematical algorithm to verify a block before adding it to the blockchain. So to add a block of transaction to the chain, each person maintaining a ledger or a copy of the file must solve a special kind of math problem created by a hash function, which is a function that generates an output that's it easily generates an output, but it's really hard to find the input. So this is the math problem that has to be solved in order to verify a transaction. And Bitcoin was designed using, it was a choice of the creator, using the secure hash algorithm 256-bit. So it was developed by the United States and as an encryption method. And it takes computers specifically designed to solve this type of algorithm around 10 minutes to guess the solution to each problem. So billions and billions of guesses must be computed to find the right one. And the first computer to solve the hash problem gets to add the next block of transaction to the blockchain.
Okay, so to keep the blockchain secure and working properly, so independently from a third party, miners are needed. It is expensive to mine Bitcoin since the machines used must be running for long periods of time and require a lot of power. So it would cost miners a lot of, in terms of electricity bills. Therefore, a reward system was created to encourage the miners not to stop their activity. So for every block added to the blockchain, a reward is given. In 2009, the reward consisted of 50 Bitcoins. Today, in 2021, the reward is 6.25 Bitcoin. So why has it decreased? This is what we call Bitcoin halving. So every approximately 4 years, or every 210,000 blocks added to the blockchain, the reward given to the miner is divided by 2. This was done as to prevent inflation and to keep the scarcity of the Bitcoin or of the resource, which will increase its value. And it is modeled to mimic the rate at which precious metals like gold are mined and keep its supply limited. As a fun fact, it is expected that the last Bitcoin, so the 21st million Bitcoin, will be mined around the year 2140. And this is because as the number of Bitcoins increase, or as the number of remaining Bitcoins decrease, the difficulty of the math problem that needs to be solved will increase, which is why that it will require a lot of time to have solved the last set of problems.
Okay, so mining has become a driving factor for the technological advancement in the computational world, and people starting using high performance and high efficiency computing power since a miner's chances of finding a block depends on their CPU power. So back in 2008. So to solve Bitcoin's proof of work algorithms, computational power is required to perform the repetitive tasks. Early on, around 2009, miners settled for the readily available CPUs in their computers. And as time advanced, more and more miners started competing on solving these increasingly difficult algorithms. And it meant that higher hash rates were now necessary. Hash rate meaning the rate at which it can generate and solve the hash code that I talked previously, the algorithm. And so energy efficiency became an issue. And so they then switched to the GPUs of their computers, so miners, which were better at performing repetitive tasks. And then as demand rose, supply became more efficient and targeted towards these specific needs. And they moved on to the ASIC, which is application-specific integrated circuits, around 2012 or 13. And the ASICs offer more power and better energy efficiency. And with the continuous development of technology, the most sophisticated ASICs are approximately 50 million times quicker in terms of hash rate and 1 million times more efficient than CPUs used only 11 years ago.
Okay, so now we're going to take a look at the impact that Bitcoin mining has had on the environment. So naturally, the efficiency and consumption of a process depends heavily on the type of hardware used, the cooling factors, the geographical location, and other factors. For now, we are going to present some numbers and figures to show how much of an impact Bitcoin mining specifically has on the environment. And we've chosen Bitcoin because of its high popularity and price, combined with the complex and energy demanding system of proof of work, which makes it the most let's say polluting, or the cryptocurrency with the biggest effect on the environment. So starting off with the first chart, which is the Bitcoin energy consumption index chart, which shows the annualized levels of consumption of electricity used for Bitcoin mining. At the time that we wrote the paper, the Bitcoin value was around 50,000, and the levels of energy used were around 78. And as you can see, there was a long stretch where it remained at 78 terawatt hours per year. But in the last month, the value of Bitcoin has increased a lot and has reached around $62,000. And you can see this rise in price linked to the rise in the levels of consumption, since more and more miners have decided to join the competition and try to get the Bitcoin first. To put this level of consumption into perspective, we could compare it to the consumption of other industries, such as the electrical vehicles industry, which used 58 terawatt hours in 2018. So you can see that there's a big difference between the two.
I cannot hear you anymore, Karim.
Yes, Sharif, next slide.
Sorry, I lost connection for a bit. Can you hear me?
Okay, yes.
Okay, so I'm not sure where Karim ended, but here's the energy consumption by country, so per year. And as you can see, Bitcoin is now placed at the 34th place, just after the Netherlands. So when we did this report, Bitcoin was at the 39th position in terms of consumption compared to other countries. And it's probably gonna keep on increasing as it becomes more and more popular. And you might be thinking that this is not too impressive, seeing as the Bitcoin network is dispersed throughout the world and would be expected to have such a large amount of consumption. But we shouldn't forget that we're still at the very, very early stage of Bitcoin adoption. And so the Bitcoin network has not yet reached the level of usage that would justify such level. And a better standard of measurement can be achieved by taking the energy footprint per transaction. So that's what we did. We searched for a comparison with a traditional payment system. And although it must be remembered that these institutions, such as Visa, had centuries at its disposal to refine and optimize its footprint, we should not forget that. So taking the example of Visa, the official numbers for the year given by the company are the following. So 740,000 gigajoule, along with approximately 138 billion transactions globally. So comparing this with Bitcoin network, we find a very, very big difference. So not even close, as Visa transactions are almost 100,000 times less costly as far as electrical energy is concerned, which can be expected seeing the sheer number of transactions.
Similarly, this type of analysis and estimations have been made to visualize another type of footprint created by the Bitcoin network, and it is considered much more concerning than the power consumption. It is the carbon footprint. The carbon emissions in the process come from the source of the power provided to the mining facilities. And this is linked to its location, And this is the reason why carbon footprint is considered to be the most pressing issue for Bitcoin, because most of the mining, or 66% of the mining, takes place in China, where most of the energy originates from coal plants. Since reliable and cheap electricity is a must for profitable mining, these regions offer very attractive conditions for miners to settle. If we were to look at the numbers that we have in front of us, we can see that annually, the carbon footprint of the Bitcoin network is 47 megatons of CO2, which is comparable to the carbon footprint of Finland, for example. We've already talked about the electrical energy. And if we were to look at the single Bitcoin transaction footprints, again, the carbon footprint, we can see it to be equal to 430 kilograms of CO2, which is equivalent to the carbon footprint of almost 1 million Visa transactions. And in terms of electrical energy, the single Bitcoin transaction footprint is equivalent to the power consumption of an average US household over a whole month. Finally, even though Bitcoin holds the advantage over the traditional financial institutions that we've mentioned, such as Visa, of not generating plastic waste from credit cards, it creates electronic waste that cannot be overlooked, with the estimates floating around 11 kiloton per year, which is comparable to developed European countries such as Luxembourg. Okay, so as discussed above, hardware plays a key role in cryptocurrency because it affects it in every step of the process. We've already seen a chart which compares, which shows us the hash rate or the evolution of hash rate for the mining operations used in Bitcoin. But here we can see it compared to the price of Bitcoin itself. And from this chart, we can see that the hash rate has risen or increased at rates much quicker than the price of Bitcoin itself. So what does this mean? This means that having efficient hardware available is very important for mining, because as the number of competing miners increase, the total possible revenue does not increase. So it means that the expected revenue per person is decreasing, and this is why cost efficiency becomes the key in surviving in the business. So only the most efficient mining units will remain economically profitable, if the price of electricity is the same, obviously, since the older units will be functioning at a loss and would then be stopped. So what else can also help in making these mining units as efficient as possible? Well, a huge part of this rests on the cooling infrastructure. So as the machines start processing the data, it requires electrical power, which will then be converted into heat. In the case of the CPUs of our personal computers, the fans provide enough cooling. But in the case of specialized mining centers, it becomes much more challenging. Okay, so in the next step, we will now look at the two essential concepts of cooling that are used in these centers: air distribution and the refrigeration cycle.
Okay, so this is a table that presents the 9 types of air distribution usually used in room-based cooling and in data centers, so recently. And as seen in the table, the different types of distribution are flooded, targeted, and contained. And these can be applied to the supply or to the return, and efficiency varies based on the combination. So flooded indicates that there is no envelope to direct the airflow in any particular way, and allows for air mixing, whereas targeted means that the supply or return flow is located within 3 meters of the mining units, which are generating heat. Air mixing is still happening, but at a lesser extent. And finally, the contained means that the flows are completely isolated and do not mix. So as they go through specific containers. The most energy efficient installation found here is the flooded supply with contained return, as it can absorb 70 to 100% of the mining equipment exhaust heat, and it can be coupled with an yes, so it's 70 to 100% of mining equipment exhaust heat. Okay, sorry, my bad. And it's the one on the upper right. And recently, Google has started implementing such type of air distribution in its data centers.
Okay, so as for the refrigeration cycle, it is just the regular cycle found in a heat pump circuit. So the refrigerant absorbs the heat from the mining equipment air, and then it transports it to a cooling unit. So as an example, we've shown here the computer room air conditioning setup, which is the most used setup in small to medium-sized mining operations. So most of the cycle is located indoors, so inside the room, where we find the usual components of the refrigeration cycle. So it's the compressor, the evaporator, and the expansion valve, with the remaining component, which is the condenser, located outdoors, on the building roof, for example, where the heat is being rejected as the refrigerant is cooled by ambient air. Next slide.
So with the increasing popularity, an increasing number of miners are trying to establish themselves in the market. And we have already seen how hardware efficiency is key in optimizing this process, but there are other factors that can be modified to have a competitive edge, such as the price of electricity. So the search for cheap electricity has led most miners to China, where it's estimated that nearly 66% of the global mining takes place. And effectively, only 10% or almost 10% of the world's Bitcoin mining in China is cheap because of the hydropowered plants available in a specific region. And the main issue of having renewables generate the power needed for the mining is that the quasi-constant demand of energy required by the mining facilities cannot be met all year long by the fluctuating renewable supply. And effectively, these processors keep on working day and night at the same rate until they become unprofitable or they're switched off or break down. And this deficit is filled through traditional carbon emitting sources. For example, there is almost 3 times less power available during a dry season in the Chinese hydropower plants. But some environmentally friendly miners have settled in places like Canada, Iceland, and Sweden, where the cool weather and the abundance of renewable energy has led to very low levels of carbon intensity compared to China or the US. And it can go as low as 0 grams of CO2 equivalent per kilowatt hour in Iceland, for example, as seen in the chart below. And in more extreme cases, we've seen the first Arctic crypto mining facility set up in the Siberian city, which offers 2 key criteria needed for positive results, which is the very low temperatures up to minus 40 degrees Celsius to efficiently cool the machines, and cheap electricity of around $0.04 US per kilowatt hour generated from hydropower or gas.
Okay, so while those efforts to integrate more renewable energy into the Bitcoin network are promising, the numbers indicate that it is not being done at a rate that compares to that of the non-renewable powered facilities. So you can see here in the graph where the darker colors represent the non-renewable share and the lighter colors represent the renewable share. You can clearly see that the non-renewable share is actually increasing with respect to the renewable share. Next slide, please. So now we're going to take a look at 2 case studies, the first one being wind farms and mining. So in this case study, we can see that in emerging countries such as Brazil, more and more renewable power plants are being built. But there is a problem, since there is a time lag between the end of construction of the power plant and their entry into the regulated market, where they can start selling the electricity that they produce. So usually in this gap, or in those 4 years or more, they sell their energy that they produce into what we call the free market. So here we're proposing a solution, or a solution has been proposed of having a mining farm also built on the same location and using this energy that is produced not to sell on the, not to be sold on the free market, but actually to be used in mining Bitcoin, for example. So three types of scenarios were used, and simulations were ran to find what types of NPV or net present value would be found. So the first scenario being that all of the electricity that is produced in this 4 years are sold on the free market. The second one being that a mining farm is built and it is used for 2 years, for the first 2 years. Since then, after those 2 years, the mining equipment would become obsolete. And the third scenario being that after the first 2 years, the mining equipment is actually renewed and bought again and used for the next 2 years. And you can clearly see from the numbers here that in the third scenario, we have the highest NPV and the lowest probability of a negative NPV, meaning that the third scenario where we're buying into the mining operations would have the most profitable outcome.
Okay, so in our second case study, we wanted to see if whether Bitcoin mining has the potential to replace, whether it could provide enough heat required to maintain an indoor temperature of a house. So not really act as a heating method, but if it can provide the quantity of heat needed. So we took an example of a house. We had the dimensions, so it was 40 foot by 40, and we had the R values of the walls and of the roof and everything needed. So we assumed that the indoor temperature we wanted to maintain was 20 degrees Celsius, and the outdoor temperature was minus 15 degrees Celsius, which is pretty extreme, you know? So we assumed it was in Finland, used the Finnish electricity cost, and we relied on the hardware that's called Antminer S19 Pro, and here are the specifications. So the power consumption, the hash rate, the price, and the heat production. And so we, at the time of our study, one Bitcoin was around 49,000 or 50,000, and today it's 62. Just to let you know how fluctuating, how it fluctuates, and using the CryptoCompare website, we were able to find out using the specific hash rate of our machine how much we could generate profit by mining Bitcoin. We got around $5,000 per year, and so we computed also the operating costs per day using the Finnish electricity cost, and we found out that okay, before finding out, we also computed the required heat to maintain the temperature of our house using what we learned in class, and it was around 13,000 BTU. And we found out that using a traditional heating electrical heater, actually we would need two of those that we considered. It would cost us 80 cents per hour, whereas using the Antminer would cost us, actually would profit us 60 cents per hour, all while providing around 2/3 of the required heat. So it didn't provide enough heat, but it did provide 60 cents of profit per hour, which is non-negligible. So having $5,000 in profit per year, the payback period of the hardware would be 1 year and 2 months. And it's estimated that around the lifetime of the hardware is 2.5 years. And so this leaves us with, in 2.5 years, $7,000 in profit and 2/3 of heating quantity required for the house. So there's an infinity of combinations that we could have done. مثلا, we could have tried with 2 Antminers. We would have probably have better results. But just to let you know that even one can provide 2/3 of the heat required with a massive profit.
Okay, so in conclusion, from the data that we've collected, it is clear that the worry surrounding this phenomenon is warranted, especially considering that these figures will continue to rise with time as the popularity and the price of Bitcoin grows. Also, we've seen that although renewable energy efforts have been made in this field, these efforts seem lacking and will necessitate ramping up to stay effective. The appeal in Bitcoin mining lies in its flexibility and profitability, because it can be coupled to a wide array of activities, as we've seen in the wind farm study. And it could also develop in the coming years a new type of usage, like its heating capability, as demonstrated in the second case study. Thank you.
Thank you.
Thank you for this presentation. Look, I will I will open the questions for students in case anyone want to ask something. So any question on
yes,
this
I have
work?
a question.
Okay, yeah, go. What's
Yes,
your name?
first of all,
Please, your
my
name.
name,
Yeah.
Mark Matar.
Okay.
Yes, first of all, thank you for the very interesting presentation. I have a question. Are all the cryptocurrencies this harmful to the environment, or are some exceptions?
Okay, I'll be answering. Thank you, Mark, for the question. So the simple answer is no, because as Sharif mentioned in the blockchain slide, and if you could go back to the slide 7, the system on which Bitcoin is built is called proof of work, and in this proof of work system, this is what necessitates the huge number of attempts to be able to solve the problem and gain the reward. But this system is not used in all cryptocurrencies. And nowadays, more and more cryptocurrencies are using what is called a proof of stake system. And without going too much into the details, it's different from this, and it's not harmful at all for the environment. So many have called for Bitcoin to change its system and go to proof of stake. But the disadvantage of this is that proof of work is much more secure in terms of hacking, which is why Bitcoin has decided to remain on its proof of work system, which is more harmful to the environment. So there is some type of disadvantage changing, but this is why not all cryptocurrencies are this harmful.
And it's
okay.
also a different
financial
model. It's a different financial model too. It depends on what they agree with more, like the adopters of cryptocurrencies.
The time
Okay,
of the Zoom
thank
meeting
you.
will end.
That was your question, Mark? Mike?
Yes.
Okay. So I will open a new
Thank you.
session to continue the question, okay?
Okay.